Okay. Okay, so shall we start? You can react to it like thumbs up or something. Okay. Okay, so our agenda for today is to look into what quantum physics exactly is. And first of all, we need to know why we need quantum physics. So we need to know why classical physics, classical theory or the classical physics got proven wrong, and why did we end up jumping to quantum physics? Like, why is everything happening in the first place? So our agenda for today is to look into all of the theories. So what everyone, all the scientists suggested, how the classical theory got proved wrong, and then what did Planck, and then eventually de Broglie, then Schrödinger's, all the equations that we'll be looking into, and then finally Fermi Dirac statistics. And yeah, we'll be looking into all of this. So first we'll start with classical physics. So what does classical physics actually say? So classical physics, it just assumed everything to exist. Like, let's say when you just throw a ball at some time, so it is telling that I can find the position of the ball. I can find the momentum of the ball. We all studied, no? We all studied in our 12th grade. As in, I am able to find where exactly the ball is. But so everyone, all of them thought everything in physics is just done and dusted. You need not find anything else. There is nothing to discover or there's nothing more at all. So, but eventually what everyone noticed is that for microscopic level, this need not work and this doesn't work specifically. So that's why quantum physics actually came into picture. But yeah, so this classical physics, so this theory of electromagnetism, so Maxwell's electromagnetism, it provided framework for to study radiation. So how matter and radiation are described in terms of particles and waves. So everyone thought that there is wave that exists, but eventually we found that particle nature also exists. No, so in that case, you need to come up with photoelectric effect, then only everything started coming up. So it was not all fancy, you're not all done with the entire of physics. So yeah, as for the interaction between matter and radiation, they were well defined by the thermodynamics. In terms of matter waves and radiation, it was well explained. But if you see later, we'll deal with something called as black body radiation. Okay, that is proving something wrong. So we'll be looking into what is black body radiation and why did it prove classical theory wrong also. Okay, so yeah, now the origin of quantum physics. So Einstein's relativity theory. So one second, I'm so sorry. Okay, yeah, sorry. So Einstein, he actually talked about Newtonic mechanics that sees at very high speeds. So at high speeds, even the speed that is more than the light itself, at that time, the classical theory fails. So this is something that led to quantum physics. And then there is microscopic domain. I said, right, for macro particles, all of the determining time, the momentum, the speed, the exact position, that is possible. But here in a microscopic level, it doesn't actually, so it need not work. So physics sees it at microscopic level. Okay. So then comes something called as black body radiation. We'll look into it soon. Okay. So thermal radiation. it was questionable due to some experimental observations related to thermal radiation. So why cannot we see any object to glow? So you should be able to see every object that is glowing, no? Actually, the point behind is you can't really see some macro objects glowing. So like you can't see your chair glowing or something like that, no? Because like objects which is at room temperature, they radiate at infrared region. So in that case, humans can't really see. So you can only see it with IR cameras. So that IR cameras uses the concept of thermal radiation so that you get to see stuff. So yeah, that is it with this. Okay, so how can we detect thermal radiation? So when you incident, then there is some amount of. Can you hear me all? I'm audible, right? You can react with. Okay, okay. So the problem with any particle in general, no. So every particle will have some some different absorption levels and emission levels. So each material will differ in its properties in terms of absorption and emission levels. So on all your experiments, you won't get like a proper result. So that's why black body came into picture. So in case of black body, it's a perfect absorber as well as a perfect emitter. Okay, so the radiation that is coming out of the black body, the thermal radiation that is coming is called as black body radiation. We'll soon even look into more about this. So if you see here, the if this is the narrow orifice over here, the narrow slit over here, that is considered to be a black body. So when there is some amount of uh, there's some incident ray going in, then all of it gets bounced back and it gets observed fully. Okay, so nothing is like transmitted out in an ideal black body, which I'm talking about. Okay, so So black body is a spherical polished cavity, blackened inside and completely closed except for an narrow orifice. That's just the definition of what black body is. So the absorptive power, the A lambda, it is the heat absorbed by the body by the heat incident on the body. So it is actually between 0 and 1. If it is 1, that is proper black body, like an ideal black body which observes everything. If A lambda is equal to 1, in that case, it observes everything. So that is like a proper ideal black body condition. So I told you before, right? There is zero reflection or no emission, and there is zero transmittance. Everything that goes inside gets perfectly absorbed. Okay, so that is all with this. So black body means it need not be just black body. So I mean, it's just not black. Okay, it's not like uh, how do I say? So to give an example over here, there is a wire in the silver color. Then first it gives red and then yellow. Then it goes on with all of its colors, no? As it becomes more, as it gets heated, as temperature is increased on it. So that is just an example. So there are multiple examples of black bodies over here. Okay, and then over here there's black body radiation. So they're just telling that there is some material which is X and then Y. So they're starting from one particular temperature over here. So they're starting at one particular temperature and then X with time, it cools much more faster than Y. That is what they're telling. So the temperature of X is falling rapidly. So X is cooling much more faster. So if it's cooling much more faster, that means it will emit more heat, no, per unit time. So this is X, which is cooling much more faster than Y. That means it emits more. In our case over here, X emits more heat per unit. Okay, I'm not able to see. Okay, so if it's able to emit more heat per unit time, that means it is also a good observer. If it, like by Kirchhoff's law, no. So if you can emit, if you are a good emitter, you are also a good observer. So the emission power for X is very high, and similarly, the absorption power of X is also high by Kirchhoff's law, no. So hence, you can say that A of X, so that is the absorptive power that we saw right now. That is the heat absorbed by body. Okay. So the heat absorbed by the body by the heat incident on body. So the absorptive power of X is also high. So hence we are saying that A of X is greater than A of Y. Is everything clear till now? Okay. Please stop me if I'm going like very fast or something like that. Okay, then there comes experimental observation about black body radiation. So the scientists actually saw how much energy like the black body radiates in each frequency. So the spectral energy density, that is basically how much energy the black body radiates. Okay, so in some particular frequency. So if you see that it gave a bell-shaped curve as such. Okay, so to each frequency there corresponds an energy density. To each frequency, there corresponds an energy density that is independent of the chemical composition of the body. It only depends on the temperature. So frequency is just 1 by T. No? So it depends only on the temperature. So it's it doesn't depend on any of the composition of the particle in itself. So then the observation made was like each frequency has specific energy density value is what we saw till now. And it only depends on the temperature, right? So then is any doubts? Okay, oh, okay, fine. So the energy density, so if you see notice the graph here, it first starts from 0 and then it reaches the peak at one particular frequency. Let's uh, probably call that as V max or something. I mean, new max, it's frequency. So new max, and then it decreases, and then it just decays off, right? So what does this mean? So black body does not emit equally at all frequencies. So at some frequency, it tends to decay also. It's not always, it does not always emit at all frequency is what it says here from the graph also. Okay, so it reaches a maximum or fixed value of frequency V max, and then it decreases continuously with further increase in frequency. So with increase in frequency over here, our spectral energy density decays, right? So what does it tell is that black body does not emit equally at all frequencies. So then okay, then the area under the curve. So area under this curve will talk about the intensity, right? So the area under the curve will talk about intensity. So what do you express intensity as? Intensity is basically power by area, right? So what is power? That is energy by time, or here you're representing it as Q. I mean, still works. Q by AT. So this is your intensity. Okay. So if you see here, Also, if you see, notice this graph, it is in terms of frequency, but if you change it in terms of temperature, okay, so if there is an increase in temperature, the radiation also increases. So actually, Stefan Boltzmann actually said that the intensity is proportional to T power 4. That is the temperature power 4. That is what Stefan Boltzmann said. It didn't talk about firstly, it didn't talk about the frequency in itself. So it only talked about the temperature relation. Okay, so the intensity is proportional to the temperature. And later it was said that the energy with increase in radiation, the frequency also changes. So accordingly, we got this bell-shaped graph. So that is what this is. So the graph area is proportional to T power 4. So what is the graph area? It is basically the intensity. So intensity, we know that it is Q by AT. That is also proportional to T power 4, which is the temperature. So we can just have like a constant and then so intensity is equal to sigma T power 4. So yeah, E is the emissivity. There's a for other bodies. Okay, if it is not a black body, then E is the emissivity. Okay, so now let's just do this small problem here. So they gave our power to be 6,000 watt. They gave our area to be 0.1 meter square. We have to find the temperature and then we know the value. Okay, so now we know that, okay, how do we get all of this formulas? It's just from the same thing which I already told you. So power is essentially, we know that intensity is power by area, right? So power by area is actually sigma T power 4. So if you get A to the other side, you get just power is equal to sigma A T power 4. So this is it. So you just substitute the value, you know sigma, you know A, and you know P. So you'll get T. Is everything clear till now?
Yep.
Okay. Okay. Then, okay, now we'll be looking into ultraviolet catastrophe and all those now. Okay, if you see here, okay, now there are two curves over here, three curves, two more curves here. So as the temperature curve is taller, like if it becomes taller and more broader, there is more energy also. Okay, let's say when if there's more energy density, then there's more temperature and there's more radiation. No, in that case, as the temperature increases, you also see that the intensity becomes broader and broader, as in the area under the curve becomes broader and broader, right? So even if you see here, T1 is less than T2, less than T3. That is what they're coming to say here. So your peak, it shifts towards the right. If you see here, it is just here. But as your temperature increases, your Vmax shifts towards your right. That is the observation that you can get from this graph. It shifts towards your right. Okay, and then comes Wein's displacement law. So what did Wein say? So he said that the lambda is inversely proportional to T. Okay, so, and the constant was B. Lambda was inversely proportional to T is what he said. Okay, so now let's just look at this maybe. So they're asking what is the correct options here. So lambda 1 is smaller. Okay, so that's like a smaller wavelength. And then for lambda 1, the corresponding temperature is T1. For lambda 2, it's T2. Lambda 3 is T3. So here, if you see, lambda 1 is less than lambda 2, and then lambda 2 is less than lambda 3. So your temperature should be exactly the opposite, no? Because lambda is proportional to 1 by T. So this should be a relation, and hence it should be option A, right? Okay, now this thing is you need to just know it for theory purposes. But the idea behind this is, so the radiations are modeled as tiny oscillators called atoms. So back then they didn't even discover atoms, so it was just considered as some tiny oscillations. So that is what the caused the radiation, the black body radiation. So these emissions from the tiny oscillators or the atoms. So that is what caused the radiation due to the thermal energy. Okay. So each atom was modeled as a harmonic oscillator. It keeps on oscillating. And then if there's more energy, then there's more temperature given. So there's more radiation, right? So larger will be the speed of the oscillations and further will be the displacement. That is what we saw here, right? In the graph here, as we give more energy, so the displacement will be more. Like here it shifted towards the right, right? Further is the displacement. The speed will be increasing and then the displacement also increases. So we had to find average. We need to find the total energy. Okay, so so for that we will later look at the derivation for it. So for finding the total energy by first finding the average energy and multiplying it with the number of oscillators. So we'll be soon going to that. Okay. Now here we're now going to talk about Rayleigh jeans. So earlier, what did Wayne say? Wayne said that lambda is inversely proportional to your temperature. So now Rayleigh jeans, what did he say? Okay. So that is what. So he talked about something called as energy density, which is represented as U. Okay. So he talked about energy density. So he actually did came up with this formula. So there is a derivation to it. That is not like there in the questions. Maybe at the end of the session, if we have time, we can look into it. Okay. So yeah. So now let's look into this UV catastrophe. So what does it say? So let's just look into this graph first of all. So it's telling that as frequency increases. So what does this graph say? Why is this dotted line over here? So if you see here, when the frequency is getting increased, if you move towards like this, your frequency is getting increased. So at that time, there's a dotted line which just tends to infinity, right? So what does it mean? So let's just see over here. Look at this formula over here. If this the new square becomes higher and higher, that means your energy density also becomes infinity. As your new tends to infinity, your energy density also tends to infinity. Like you can't there doesn't exist something called as infinite energy, so that's why this is called as UV catastrophe. That's why Rayleigh jeans got proved wrong in when the frequency is higher, or so when your frequency is higher, your lambda is lower, right? So how do I tell this? C is equal to new lambda. So your lambda is inversely proportional to frequency. So when in case of higher frequency, your U tends to infinity, which is not possible. It is not practically possible. So higher frequency as in okay, frequency higher, that means you're at lower wavelengths. Okay, so at shorter wavelengths, Rayleigh jeans got proved wrong. Okay, this is what we called as the UV catastrophe. So this is like a very important thing they'll ask like multiple times in exam. I don't know if they'll ask for CIA, but yeah. Okay, then Rayleigh jeans energy distribution. So here, so he considered radiation to be standing waves. Okay, so standing waves. This is how you just standing waves. Okay, and then 1 second. if you see from here, if you substitute your nu square by c cube with this formula, no, if you just rearrange it and you substitute, you will eventually get 8 pi kt by lambda per 4. So it is just like another version of the same formula, nothing new. Just that you're expressing that in terms of frequency, and now you're expressing this in terms of lambda, your wavelength. Okay, so same thing. We just saw, no, at higher frequency or lower wavelength, this fails. So let's just say lower wavelength, your lambda is lower. That means it will become 1 by 0 case, no? Like, so it will become infinity. So again, the same thing. It can't be infinity. So at lower wavelength, it doesn't work. So it fails at lower wavelength. Okay. Is everything clear till now? Is my pace fine? Okay, okay. Okay. Then comes Wein's distribution. So we will reach to this formula through the derivation that we'll be looking into later. But yeah, he just said this essentially. So for him, for shorter wavelength, it worked, but for higher wavelength, it didn't work. So just the same thing. Okay, if the wavelength is higher, if you look into this formula, that means it'll, one second, my network went. Can you hear me now? Yes. Okay. So at longer wavelength, if you see here, as the wavelength gets increased, so it just tends to infinity. And again, this is not possible. So Wein's distribution at longer wavelength, it failed. Okay. So the UV catastrophe that we talked about, the same thing. Okay. So when your lambda decreases, your when your lambda decreases, your energy density increases. That is, it tends to infinity, which is impossible, right? So it is just too high for a UV region. You can't, for ultraviolet region, it is not possible. So that's why this theory got proved wrong. So actually earlier in classical theory, it said that the average energy is proportional to kT. Now, in case you will find there is there is this ultraviolet catastrophe that is happening. So eventually you should end up with zero over here. Okay, that is a case that you have to consider, which the classical theory did consider. Okay, so yeah. So the origin on this failure, it was found on an erroneous premise that the energy exchange between radiation and matter is continuous. So they said that energy is always continuous. The energy is always continuous. You can't like break it, or you can't find something that's at a particular point. But that is what got proved wrong later. So when it comes to microscopic particle, so Planck, what he did was he actually made it into discrete particles. So he sampled the whole thing, and then he found the average energy. Okay, so this was the failure of classical energy, and then we came to the, yeah, and then only we came to the quantum. So yeah, this is it. Okay, now a question. Okay, what does it say? The lambda max of sun is 510 nanometer, and for lambda max for North Star is 350 nanometer. Okay. So they're asking in terms of temperature. So what is the thing that relates temperature and lambda? What is the thing? Wayne's law, no? So Wayne's law is basically uh, proportional to or it's equal to B by T is what we saw. Actually equal to instead of proportional, but yeah. So if you need to find T sun by T north star, then you have to essentially do the opposite, right? So it is lambda northern star by lambda sun. That is what you have to do. You will just substitute the values, do the math, and you'll get the answer. Is this fine? This works, right? Can I move to the next topic? Okay. Okay, now, yeah, this is what I was saying. There's a derivation for this, why we ended up in this. For now, we'll just skip it. After when we have time, we'll come back. Okay. So, yeah, the black body theoretical approach. This is what I said before. So here, I told you, know, classical theory, it said that our average energy, it is actually kT. Okay, that is what our classical theory said. But now, when we saw, right, at higher frequency, our energy density also becomes higher, and that was our UV catastrophe case. So we have to somehow make the energy zero instead of like it being to infinity. That cannot work like that way, no? So that is what is the case that classical theory didn't consider. Okay, and that's why it led to the UV catastrophe condition. So what they did was they consider classical theory consider everything to be a continuous distribution. So now Planck, what he did was he just made everything discrete. So he sampled the whole graph per se. So just sampling. Okay, 1 second. Why is the same thing? Okay. So Planck actually sampled everything. So actually it's just sampling. So I just had to skip everything. It's nothing much. From this continuous wave, they are just making into discrete. They're just dividing it. That's all. So the first 3 points we already looked into. Now, so the Planck hypothesis says that everything is an integral multiple of frequency. The energy is an integral multiple of frequency. So E is equal to NH nu is what Planck said. So that's why he sampled the continuous distribution. Then if you see here, it was continuous and then he made it into discrete. So then he wanted to find the energy. You know, so why are we doing all of this? We need to find the earlier also even that graph that he looked into, it was energy spectral energy distribution by frequency. But it did fail at one point because of the I mean this is the dotted line, okay? So it did fail at one point. So now we have to find the energy, total energy. So to find total energy, that is basically average energy by the number of oscillators. So first we need to find the average energy, no? So that's what we are going to look into now. This is like a very important thing that you have to learn, the derivation. Okay. So first so our aim now is to find the total energy. So to find the total energy, we need to find average energy by the number of oscillators in each frequency range. So he divided everything into several frequency ranges, right? So as discrete particles. So into find the total energy now. Okay. So to find total, now we'll first look into average energy. So for the average energy, he used something called as Boltzmann statistics. So the Boltzmann statistics, there's actually a nice derivation to it. it will actually end up in Ni is equal to N naught e power minus Ei by kT. Okay. So he just used this Boltzmann statistics to find the number of oscillators. So I told you, right, to find the average energy, you need to find the total number of oscillations. Okay. So N1 is N naught e power minus E1 by kT. So E1 is h nu. We saw, right? Our energy is an integral multiple of frequency. So E is equal to h nu. H is the proportionality constant over here. So h nu by kT. And then our N2 is N naught e power minus 2h2 h nu by kT and so on. Okay, so like this, if you need to find the total number of oscillators, which is N, that means you need to add all of them. So N naught plus N naught e power minus e by kT, N naught e power minus 2e by kT and so on. So yeah, in this case, if you take, they're just taking this as x just for simpler purposes. Why will I write this whole thing every single time? So I'm just taking this as x, okay? So, and I'm taking n naught common outside. So I'll end up reaching n naught into 1 plus x. So this will be our x now. And then there is a 2 here. So it's x square, x plus x cube and so on. So what is this series? So it is essentially 1 minus x 1 minus x inverse. No, so it's 1 by 1 minus x. Now, so that is the series. So we're just substituting that over here, which is essentially n naught by 1 minus x, right? Now, we found the total number of oscillators. Now we have to find the total energy density. So what is total energy density? It is basically the you need to add all of the products of number density of oscillators in each level and then the energy in each oscillator. So what is the number density in each energy level? That is your this whole thing. N naught plus N naught x plus N naught x square plus N naught x cube. That is what the number density oscillators. No, that is what the oscillators that we looked into. And then you multiply it with energy in the each level. So this is for entirely we are seeing, but in terms of finding the average energy oscillator, you need to find the energy of each oscillator and you multiply it with the number oscillators, number density of the oscillators. So 0, first it starts from 0 energy level, 0 into N naught. So N naught is the first part. I'm just expanding this expression. Okay, so it's N naught into N naught x like that. So then it is E into N naught x. So the next expression is N naught into x. No, then 2e into n naught x square, then 3e into n naught x cube, and so on. So we're just simplifying the expression now, taking n naught ex common, and then you have the remaining over here. So this series is essentially 1 by 1 minus x, the whole square. So we're just writing in terms of that. Okay, so now we are expanding 1 minus x. So 1 minus x into 1 minus x. So this is what we already found, right? The total number of oscillators. The n that we already found was this. You see here, our capital N was equal to this. Okay, our capital N was equal to n naught divided by 1 minus x. So we are just substituting n over here. And then uh, x, we are just trying to remove this x out. And then it's just 1 by x minus 1, right? So that is what we are writing it here. Nothing much, just simplification. Just trying to make everything look nice. So yeah, now we are done with finding the average energy, right? So no, we're done with, we're not done with it yet. We are done with finding the total energy. So what did I write here? Okay. So our average energy we're doing total energy by N. Did I write it different? Okay, this is wrong. Okay, the total energy by N. Okay, the total energy is this expression that we got. And then our N is the total number of oscillators. So it's total energy by N. So you'll end up getting E by X inverse minus 1. Okay, so X we just took it for simpler purposes. So our X initially was E power minus epsilon by KT. So that is what we'll substitute. Our epsilon, we already know that it is h nu. E is equal to, epsilon is equal to h nu, right? So finally, our average energy. Okay, so the average energy per oscillator is h nu by e power h nu by kt minus 1. But the total number of density states is, we saw it before, no? There was one derivation for it also. That is 8 pi 8 pi nu square d nu by cq. So to find a total energy density within that frequency, if you need to find the total energy density within some frequency, say we are just dividing it, and then if this is h1 h nu 1 and this is h nu 2, we're finding the, if you need to find the total energy density within that range, you just like multiply these two. So it's number density into the average energy. Okay, so you end up getting the energy density formula, which is what Planck derived it. Okay, so if I need to just recap it once. So first, what classical theory said that energy is a continuous distribution, but Planck just made it into discrete energy levels. So, and he told that energy is an integral multiple of frequency. So first, so to find our average energy, we need to do total energy by N, right? So we are finding our average energy. So first we use something called as Boltzmann statistics, and we express it in terms of N1, N2, and so on. So, and we added up all to get the total number of oscillators, which is N. We just added them all. We just took X for simplicity instead of writing everything. And then we used just a series. So you just simplified the whole formula and you got our total number of oscillators to be n naught by 1 minus x. Then to find the total energy, what we did was for each oscillator, and then we multiplied with the energy of each oscillator in each level. So it's 0 into n naught plus epsilon into n naught x and so on. So again, you simplified and you got you got an expression. So this total average energy is total energy by the number of oscillators. So that is your n, capital N. And then you finally, after substitution of E, X, everything, you will get h nu by E power h nu by kt minus 1. Okay. So to find the energy density, you need to multiply the average energy per oscillator into the number of density states. Okay. So that is your energy density between this frequency range. Okay, this is what Planck said. So yeah, is this derivation clear? There's nothing to memorize as such. If you just understand the flow of it, you can actually do it. Is this fine? Okay. Okay. So let's move on. So now we'll see from Planck's distribution, we'll just see how we can make vanes which works only for shorter wavelengths and Rayleigh jeans which only works for longer wavelengths. We'll just derive theirs from it. So essentially what Planck did was he derived from vanes and Rayleighs. So he combined the characteristics of both vanes and Rayleighs and then he came up with this, but we're just doing the reverse approach. Okay. So yeah. So we just saw earlier that Wein's radiation law, no, it actually failed for lower frequencies. Okay, so that is what we saw earlier. Now, Wein's law actually works for higher frequency or shorter wavelengths. So let's just consider Planck's distribution. So in case of higher frequency, so he e power h nu by kt. So e power h nu by kt, if it is higher, then it is then this in this denominator e power h nu by kt takes more precedence than 1. No, so 1 will become like a minor term or something like that. So your 1 vanishes. So it's only e power h nu by kt. That's why you don't consider the 1 over here. It's just because this is your dominating term. If when your frequency is higher, then it tends to e power infinity. That means this will be a dominating term. Okay. So then what we are essentially doing is we already know that nu is equal to c by lambda. Okay. And then if you differentiate it, it is c by lambda square d lambda. Okay. So we are substituting all of this in our formula for now, where we have made this denominator to e power h nu by kt alone. Okay, so wherever there is nu, you substitute it by c by lambda. Wherever there is d nu, that is over here, you substitute it with c by lambda square d lambda. Okay, so after you do all of that, you will end up with this. Okay, so now our c1. So this is just a constant term that we are representing as c1, and then this is also the constant term that we are representing as c2. Okay. That's all with respect to veins. So veins actually it worked for shorter wavelengths. Okay, that is the reference that you can get from this. Okay, then in for Rayleigh genes, it worked for longer wavelengths. So what does it mean? That means it's low frequency, right? Because it's inversely wavelength and frequency are inversely proportional. So again, if you go back to our Planck's, so in case of lower frequency, so if the frequency is lower, so okay, let's just write this e power x is, what is e power x? It is 1 plus x plus x square by 2 factorial, so on, no? That is what e power x is. So it goes on x cube by 3 factorial and so on. Okay, so now if you see here, when your x, I'm just considering actually in over here it is h nu by kt, which is our x, but I'm just taking the series to explain you why we ended up with 1 plus h nu by kt. Okay, so if you see this in terms when it is lower frequency, that means this entire term is very small. It is not a dominating term. So in that case, your if you consider this series also, so all of your bigger terms get ruled out, and only because your e power h nu by kt is very small, you only take the lower order terms. Okay, so you're just taking, instead of e power h nu by kt, you're just taking 1 plus x, that is e1 plus h nu by kt. Okay, and then minus 1 is there, so this 1 and 1 gets cancelled. So this is why we are doing this, just from the series. Okay, so there, since here if you see, since this e power h nu by kt was a dominating term, we just wrote that, but now it is not the dominating term, so we are seeing based on the series. Okay, then it is kt by h nu. Okay, so again we are substituting in terms of wherever there's nu, you substitute c by lambda, and then wherever there's d nu, you substitute with c d lambda by lambda square. So all of that, if you do, you'll end up with an expression in terms of your lambda. Okay, so this is what Rayleigh jeans said. So if I need to brush up, after we found the Planck's distribution for shorter wavelengths or higher frequencies, since the frequency is higher, it tends to e power infinity. So that means this is the dominating term. So we are substituting just e power h nu by kt. And then we substitute nu and d nu, and we'll get this formula for the Wien's radiation law. And this only works for higher frequency or shorter wavelengths. So for the remaining, that is for longer wavelength and lower frequency, we have Rayleigh-Jean's law. So in that case, since because lower frequency, that will be your lower order term when you express in terms of the series. So that's why you substitute it as 1 plus h nu by kt minus 1, and the 1 gets cancelled, and then you will have the remaining. Okay, so after substituting with nu and d nu, you will end up with your formula for the formula for energy density in terms of according to Rayleigh-Jeans. Okay, is this part clear? Like, it's a very important derivation that you need to know for sure. If you know the understanding behind it, you can derive it on your own also. Any doubts you can ask me. Is it fine? You can react if it's fine. Okay, I'll move on. I'll assume it's fine. So we are done with this. We first got the formula for energy density and then for Wien's and Rayleigh-Jeans. Okay, that is what we saw till now. So now all of this, okay, what is light? Okay, everything in terms of Maxwell equations, so Gauss laws in in terms of energy and then magnetic field, like electric field, magnetic field, and so on. Faraday's law, Maxwell. This is not essentially required for now. Okay, so it's all that we learned in 12th grade. Okay, so okay, what is light? Okay, so light is an electromagnetic wave. So what is an electromagnetic wave? Like a perpendicular distribution in terms of electric field and magnetic field. No, that is what light is. Okay, so now if you see, it extends from your radio waves, infrared, visible light. This is your range for it, X-rays and then gamma rays. Okay. So light is an EM wave that permits through space, vacuum, or through a medium, like travels wave propagates through a medium. So it's just an electromagnetic wave that permits through everything. Okay. So what are your characteristics of lights? So it's an electromagnetic wave, we all know. Then wave characteristics, you have wavelength, which is c by nu. Lambda is 2 pi by kt. So you just need to know all of these formulas because you might be using it in multiple occasions. You just nothing to learn. It's everything that we know as such. And then amplitude is E naught, and then spectrum. Okay, light gives us a spectrum, right? It's diffraction, interference, polarization, energy, and momentum. So all of this we'll be looking into continuous absorption and emission of EM waves. Okay, that's just something that's not really required in terms of exam perspective, but yeah. The derivation about the Planck distribution, Rayleigh-Jeans, that and all is very important. Okay, next we'll be looking into something called as photoelectric effect. So what is photoelectric effect? So essentially, when there's a light rays falling on a metallic surface, then it ejects some electrons. Okay, so that is what the essence of photoelectric effect itself is. So if you see this experimental setup, if you would want to see, like a monochromatic light is incident. This is like a vacuum tube. Okay, so this is a vacuum tube, and then your monochromatic radiation is incident, and then it hits the metal surface and the electrons gets ejected. So by this, there is a voltage. There is some variable voltage that is created because of this ejection of electrons. That is what the. That's why they see with this. They just set up this. and then they found there is a variable voltage that is there, and hence they concluded that electrons are being ejected. So yeah, so all of these formulas we need to know. Kinetic energy is EV naught. Okay, this we already know. Then okay, and then kinetic energy is EV naught, and then this formula that we should know. Kinetic energy max is h nu by h nu naught. So this h nu naught is our work function. Okay, so work function you can express in terms of phi also. Okay, so that is our h nu naught. So now here, if you see, if the frequency is less than the threshold frequency, that means you're still the it is not enough incident light for the electrons to get ejected. So there's no photoelectric effect that will take place. But if from the threshold frequency, if it is higher, the frequency that we provide is higher, then only you will notice the ejection of electrons, and then only you will see photoelectric effect taking place. Okay, so this is one kinetic energy is equal to h nu by h nu naught is something that you need to know. E is equal to h nu is something we all know. Okay, so yeah, this point is the threshold frequency that I was talking about. All right. So yeah. Okay, now there is a problem over here. Okay, we'll probably do this first question alone for now. So what does it say? So we just first list down what and all it is. The question says the ratio of the energy density of radiation at frequency nu observed at a higher temperature Th to that recorded at 300. So we need to find the ratio. Okay, sum of energy ratio of the energy density. You need to find with respect to first a temperature called Th, some temperature Th divided by energy density in at 300 Kelvin. Okay, so at 300. So this is what you have to find. So you estimate Th using Planck's radiation law. So they've told. So now it's just using Planck's distribution, the law, the formula that we already know. So instead of T, we're just substituting with TH. For our first case, we need to find energy density in terms of TH, no? So instead of KT, we're substituting it with TH. That is the first equation. Then we're substituting with 300, and that's the second equation. So we're just taking the ratio. We are deleting, we are actually cutting down all of the common terms, and we'll end up with this, right? So, and they've given that the energy density is equal to 6.36 into 10 to the power 27. So we're equating with that. So energy density, the ratio is already given. So the ratio, this value is equal to this by this. So now you use all of your logarithm formulas, and then you will end up with your final answer. So for questions like this, you need to know all of your formulas with respect to log and all those. Okay. I think this shouldn't be a matter. So all of your H values, H nu, I think H nu by KB, they've given a value for it. So yeah, all of these values, it will be given in the question in itself. So need not worry about it. Okay, now is everything fine till now? We can move to the next topic in that case.
Dhanya, I have something to say. Can you be a little more faster and you can cover the important stuff? Like,
Oh,
I mean, focus more on the important stuff. Right? You
uh,
can like dig into a few things if it is necessary in each line of the slide, but it is not
mhm.
always necessary. Just telling you because we don't have a lot of time and stop the recording now and then so that you can sort it out to different topics and upload it.
Oh, okay.
Yeah, that will also do. And is there a mechanism for you to look at the chats?
Yes, yes,
Okay,
I
so
can.
okay, yeah. I just advise all the people who are in the meeting, just tell your requirements to her so that she can customize the lecture for you. Okay, all the best people. Yeah, I just want to tell that. Thank you. Bye.
Okay, thank you. Okay. Okay, is everything fine till now?